My name's Natalie. I'm a co-founder of Gimlet Labs, and you'll learn a little bit more about what we do in a moment. So, I don't know how much academia gets exposure to the infrastructure pain points that we see in AI today, but this headline struck me a few weeks ago. You don't hear much about the AI overbuild anymore. It gave me a chuckle because I think for a while there was a lot of concern that we were collectively investing in significant data center capacity for AI that was overblown. The demand's not going to be there. We don't need this much compute, etc. And it seems like those questions and concerns have been pretty much silenced recently. So that's because the demand continues to explode. We are on track to spend $765 billion on AI CapEx this year alone. For your context, inflation adjusted, because everyone always asks about if it's inflation adjusted, that is more than we spent building out the US highway system. So that's AI CapEx in one single year. And we can see that it's going to just get dramatically more. See how small 2026 is on that chart by Goldman Sachs? And notice how that token growth only goes up to 2030, 4 years from now. So if you do the math, you'll say, okay, great, we'll just spend 15 trillion more dollars on this and we'll be set, right? There is a little bit of an interesting warning sign here, though, which is despite the fact that I can't get any GPUs, oh my God, the GPUs deployed for inference today are only utilized generally between 20 and 30%. We're spending trillions and trillions of dollars on this hardware, and yet we're not actually getting them to the utilization that you would have expected given how much demand there is. And this problem gets more complex because the applications are getting more complex. The infrastructure that we use today was built for training. It was then repurposed to run individual LLM inference, a single chat model talking to you like ChatGPT. But what's happened is those models are so good that we've plugged in tools to them. We've plugged in multiple steps to them. We've turned them into coding agents. That is a significantly more complex workload than a single LLM call. And as we see agents eating more and more of the software stack, what we're moving toward is agents talking to each other, collaborating in the background, very multi-staged, very heterogeneous, many models running at once, not just one single inference call. And so the ridiculous demand that even that middle section of workloads is imposing on our infrastructure today is causing everyone in this space to scramble and finding one of two dominant solutions, or often both. The one that you see on the left is let's use as many chips as we can. We need to use all the chips we've got, deploy it all. Every day you see Anthropic made a deal with AMD, OpenAI made a deal with TPU, whatever. Like literally every combination that exists, everyone's buying out all the capacity because we need more megawatts and we need it yesterday. The other solution you see is it seems like almost every day there's a brand new chip company that's emerged saying, we have built the chip for inference. This chip is designed for inference. It has an LLM printed into the chip. It has this, it has that. And it's going to be so much more efficient that all of these problems will go away. So at Gimlet, we came out of research at Stanford where we were looking into how to efficiently run AI inference workloads on a variety of chips. And the thing to start with there is to figure out, okay, what are the actual needs of the workload? And what you find out pretty quick as you dive into even the inference of a single LLM is that there are many different phases to that process. This is not just a uniform workload that spits out an answer. There's distinct phases and stages, each of which have different compute bottlenecks and profiles. So what we have here is on the table of like some very, very coarse grained stages, like prefill, which ingests the context and emits the first token, or tool calls, or KV cache storage. And we see all of these are extremely fundamental to agentic workloads. And yet not one of them looks quite alike in terms of the needs that it has for the hardware. What this tells us is that there is no one single chip that can be optimal for all of these phases. And that has major, major implications in terms of what we should be thinking about when we're building out trillions of dollars of CapEx for AI data centers. It's even more fine-grained than that too, because the previous chart showed very, very high-level stages of inference like prefill or decode. But actually, if you dive even deeper to the kernel level, you see that the attention kernel has different needs than the FFN and so on. And even within prefill versus decode, the same kernel in each stage has different bottlenecks. Throw in diffusion models, throw in tool calls, throw in all of these things, and you get a constellation of different points on the optimization curve. I think one thing that we're really excited about at Gimlet is the emergence of these different chips, though, because they offer different points on the trade-off curve that can match the different points on the application curve. You know, application A may have certain resource needs, but hardware A can maybe be the best fit for that resource. And so if you look at something like an SRAM-centric architecture and contrast that with a traditional GPU, I'll pick Cerebras because they just had their IPO and they're a really exciting piece of hardware. What Cerebras does is at wafer scale, they say, okay, I'm going to put as much SRAM as possible on this chip. I'm actually going to devote 50% of the chip's die to SRAM. And what that's going to do is, at the expense of compute, it's going to give me significantly better memory bandwidth. And so what you can find when you run workloads on Cerebras hardware is that for workloads that are memory bandwidth bound, they perform extremely well, fundamentally better than a GPU could perform for that same workload. This isn't because Cerebras is better than GPUs, it's just making a different set of trade-offs. So again, what we decided to do, and this is a little bit insane, I'm going to be honest, is we said, let's take this hardware. Yes, it's okay. Yeah, it's well in an insane time, right? Let's take all those different types of hardware from different vendors, different architectures, completely different types of hardware that have never been connected together, by the way. Let's co-locate them in a single data center, connect them with a high-speed fabric, and run workloads across them. Not just say run model A on hardware A and run model A on hardware B, but to say let's actually take these models, slice them up, and route each part of them to the chip that does the best at that specific part of the workload. And the result of this, and we do this for a reason, if it was 20% better, I would say don't bother, but what we find is that this delivers 3 to 10x performance, ballpark, per watt. And when you are, like us, trying to get as much data center capacity as possible, and are as power constrained as everyone in the frontier is today, getting 3 to 10x better performance per watt is a big, big deal. In order to do this, and I'm seeing the challenges of exporting from Figma to PowerPoint here, we built a software stack that intelligently takes each request. So Natalie's talking to Codex and asking it to solve some kind of coding problem for her. It will slice it up into small bits. It's not just doing things like prefill on this chip and decode on this chip. It's actually saying, let's run this kernel over here, and then it's very, deeply routed to this chip over here. And we slice it up, we distribute it, and we orchestrate it across all of this hardware. And we think that this is going to be the foundation of future data centers because the performance is just so much better and the needs of agentic inference are so big that we have to be more efficient and performant with how we're generating these tokens. So you'll see this plot from Jensen from NVIDIA quite a lot, and it basically plots the Pareto frontier of token throughput per watt versus interactivity for a given user. And so you would think, oh, that's interesting because I would have expected that token throughput and how quickly each user gets a token would be correlated with each other. But it's actually they're inversely correlated because the y-axis here reduces to basically tokens per joule. How many tokens can I produce for each joule of energy? And then the x-axis correlates to, as I'm talking to my agent, how quickly am I personally getting tokens out? And what you find is that the faster I get my tokens, the more energy I had to spend in making each of those tokens. And so what you see is that these things are on a frontier where you have to pick a trade-off point. You have to say, my application needs 500 tokens per second. So at that interactivity level, this is the throughput that I can serve per watt in my data centers. So our goal at Gimlet is to push this frontier out to up and to the right as much as we can. So if you look at something like the blue line, this would correspond to a GPU. It's extremely efficient at high throughput operations, but the interactivity drops off because it doesn't have the properties that, for example, an architecture like an a Cerebrus would have in terms of serving extremely low latency tokens. But it's really, really good at those high throughput tasks. Then the purple would correspond to something like one of those SRAM-centric architectures that I mentioned. Those chips don't have that same ability to deliver extremely, extremely energy efficient tokens, but what they do have is the ability to deliver very fast tokens. So what we can do is say, let's take the best of both worlds. Let's use each tool for the part of the job that it's the most relevant, and when we combine them together, we get something like the green line. This is a challenging thing, and I'm not going to be able to cover it all in the remaining 4 minutes, but I just want to highlight some of the interesting technical questions that we have to answer along the way to solve this problem. And if these are interesting to you, we should talk. The first one is, what are the cut lines of my workload? How do I take a model or an agent, which may be composed of many models, and decide this is the point where I slice it, where I run this part on a different chip than another part? Every slice presents an overhead because I have to do some kind of transfer of the data and the context between the chips. But then the difference in the performance is dramatic enough between those two slices that trade-off becomes worth it. So knowing what are the right cut points is an incredibly important question, and that's not an easy one. The next question we have to answer is, how do we take a given slice of that workload and lower it and optimize it to the most optimal performance on the target hardware? And then the last one would be, okay, I have each slice running on all of my target hardware. How can I, with high performance and scale, route all of my requests in prod traffic across all of these different chips with the redundancy and connectivity that they need? Because sometimes you're taking a single model and splitting it across many, many, many different chips at once. And so it needs to be resilient and it needs to be fast. So I'd like to dive into a specific example here. But before I do, I need to give a quick primer on something called speculative decoding. So in Inference, there's 2 stages, prefill and decode, like I mentioned. Prefill is the one that takes in all of the context and all of your input, and then it thinks for a while, and then it outputs that first token. Decode is a stage that it outputs every subsequent token after that. And the important thing about decode is that it needs to know the result of the last token before it can start computing the next token. This means that for very large models, because each model needs to run every single time for decode, then you can end up with a lot of that time spent in decode because it can't actually batch all the tokens together like you can for prefill. So what people have figured out is you don't actually need that full model for decode every single time. What you can do instead is say, take something like a smaller draft model. It will make guesses about tokens. Those guesses will sometimes be right. And instead of validating each token one by one, I can take 5 of them at once and say, yes, 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 no, no, or something like that with my bigger model. And so this basically changes the equation of the resource consumption needs of the workload to be much better at using compute efficiently. So what we did was we said, okay, so draft models are small. And one interesting thing about some of the new chips out there is that they're really, really good at running small models because, for example, D-Matrix Corsair has a lot of on-chip SRAM. And so if I can put all of my model weights in memory, that means that that model will be extremely fast. It's much faster than constantly paging the model weights in and out of HBM. And so what we did was we said, let's compare 3 configurations. The first one is a very vanilla prefill decode disaggregation, where we run all of the prefill on one GPU and all of the decode on another GPU. We then contrast it with a speculative decode workflow with that same GPU-only deployment. Every single one of these phases is also run on GPU. And then finally, we contrast that with taking prefill and verify, which are both run on GPU because they're both compute-bound, and then take the speculative decoder and run that on D-Matrix Corsair to see, when we mix and match different hardware together, what kind of results can we get. So let's take the results for a single request. What we can see is in the prefill decode phase, most of that time is spent in that blue, which is the decode. That's really, really long time to spend in that one phase. And then when we go down to adding speculative decoding, this one is still GPU, we cut the time down from about 25 seconds to 5 seconds. So this is a great speed up, and this is why pretty much every frontier lab uses speculative decoders. But what we can see is that if we offload the speculative decoder from the GPU in the second bar to D-matrix in the third bar, that blue section shrinks even more dramatically. It's another 3x speedup on an already highly optimized baseline. When we plot the Pareto of this, we can see that this offers us many better points of trade-off on the curve. If that user says, I want to get 1,000 tokens per second, no problem. We can do that at 60,000 tokens per second per kilowatt, I think is what it says. Or if the user says, I'm okay with 600 or 800, then it can be even more throughput than that. This is all about giving users choice. Different applications have different needs. I don't necessarily need super fast tokens for every workload. I don't necessarily need super high throughput for every workload. But what I would like to do is be able to target a superior point on these trade-off curves so that I can use the available resources much more efficiently. So thank you for listening, and also thank you to 645 Ventures for introducing us to Cornell Tech. Very happy to be here and happy to talk after to anyone. Thanks.